5.4 is now about integrating with logarithmic functions. And we talked a little bit about this when we introduced the fact that the derivative of the natural log of x is 1 over x. And we talked about how natural log of x has a domain restriction, that x has to be greater than 0, and that 1 over x has a domain restriction, that x is not allowed to be 0. And we said to remedy this, we just need to make sure we have a tool to use this, and that tool is absolute value. And the reason that we can use that tool, or the reason that that tool helps us in this situation, is that it ensures that every value we put into natural log is positive, because that's what needs to happen. If I'm starting with integration and I'm starting with something that doesn't have a natural log, I need to make sure that the only values I'm allowed to put back into the original function are positive, since that original function is going to be natural log. So we have stated this before, but this is the key part of the first half of these notes. The integral of 1 over x dx is the natural log of the absolute value of x plus c. Remember that if you have multiple functions going on, in functions within functions, or you're applying the chain rule, that this second one with u's is going to come into play. So the integral of u prime over u du is equal to the natural log of u plus c. So let's look at an example. We have the integral of x over x plus 1 squared dx, and we're evaluating this integral. So some of you probably see right away that you can undo the chain rule here and you can jump straight to the answer. But I'm going to assume, especially since this is the first time we've dealt with natural log, I'm going to assume that many of you don't see that. So I'm going to do u-substitution. But if you see the fact that you can reverse the chain rule here, go for it and do it that way. So I'm going to let u equal x squared plus 1. So du equals 2x dx. I'm going to do some substitution here. So this is going to become the integral of x times u to the negative first power times du over 2x. And then here my x's are going to cross off. And that's where I'm saying, some of you might have seen at the very beginning that you could have thrown a 1/2 and a 2 in there and then not had to do this. But that's okay. If you didn't see that, we're doing it as if you didn't see that. So this would give me the integral of u to the negative first power du. Based on this property in green up here, the integral of 1 over x dx is natural log of x. So this is going to be natural log of the absolute value of u plus c. Don't forget, you need to substitute back in whatever u was. So this is going to be the natural log of the quantity x plus 1 squared inside absolute value plus c. Something I want you to notice on this particular problem here, this absolute value is a little bit redundant. No matter what, if I square something and add 1, that's always going to be positive. So you are more than welcome to rewrite this like this. Just noticing that obviously it's already going to be positive, so I don't have to say the absolute value. And I totally left off my 1 here. This should be 1/2 times this, which means this should be 1/2, which means this should be 1/2. Shame on me. I apologize. So there is never a circumstance where you will have to get rid of absolute value. I'm just saying that sometimes you can. Again, there will never be a circumstance where you have to get rid of absolute value. I'm just pointing out that sometimes you can because it's redundant. The thing that's there is always going to be positive anyways. And the purpose of having absolute value is so that we make sure we're getting rid of any instance where the domain restriction would come into play. Let's work through a couple of examples together, and then I'm going to recommend that you pause your video and see if you can work through the rest on your own. One thing that I want to remind you is, even though this section is about natural log, or the top of this section is about integrating with natural log, remember all of the things that you have learned about integration. Just because this section is focusing on logarithms doesn't mean all the other tools you have learned for integration up to this point have left. So just be aware, think through every problem as you start. So number 1, I could really rewrite this as 5 times the integral of 1 over x dx. And that would give me 5 natural log absolute value of x plus c. Now, for number 2, this is one that's really easy to see undoing the chain rule on. If you think about the bottom of the fraction, the derivative of the bottom of the fraction is 3. So if I had a 3 up here in the numerator, I could just undo the chain rule and my life would be easier. And I can put a 3 there by putting a 1/3 in front. So now if I integrate this, this would become 1/3 times the natural log of the absolute value of 3x minus 2 plus c. If you didn't see that, you would need to use u-substitution. You would let u equal 3x minus 2. So du would equal 3 dx, which means that you would substitute in du over 3, and that's where your 1/3 would come in. You would end up with the integral of 1 over u du times 1/3. So you can use u-substitution. If you can get past needing to on simple problems like number 2, it's going to save you time. So I just did one reverse chain problem that way. On number 3, you can use the reverse chain rule again because the derivative of the denominator is going to be negative 3x squared. However, I just did one that way, so I'm going to do it u-substitution on number 3. But again, if you see reversing the chain rule, go with that. That is a great shortcut to save yourself some time. So I'm going to let u equal 3 minus x to the 3rd. So du equals negative 3x squared dx. So I can rewrite this integral as x squared times u to the negative 1st times du over negative 3x squared. So the x squareds are going to cross off. I'm going to get negative 1/3 times the integral of 1 over u du, which is going to be negative 1/3. And I'm going to go directly into substituting back in because I'm out of space here. 3 minus x squared plus c. Don't forget your plus c. Okay, go ahead and pause the video. See if you can work through 4 through 6. Remember that not every problem is going to be a natural log problem. Some of them might involve it and some of them might not. But one thing to notice is if your degree of the numerator is exactly 1 less than the degree of the denominator, that's when your natural log is typically going to come in. So keep that in mind when you are working through these problems. Go ahead, pause the video, work through 4, 5, and 6. So on number 4, you can reverse the chain rule. You can also use u-substitution. So that's going to give you that u is 9 minus x squared, du is negative 2x dx. When you do that substitution, the x's are going to go away. So I'm going to have negative 1/2 times u to the power of positive 1/2 times 2. So I'm going to say times 2, and I'm going to substitute u back in, 9 minus x squared to the positive 1/2 plus c. And obviously this 2 and 1/2 could multiply to be negative 1. So I could have negative 9 minus x squared to the power of 1/2. So no natural log involved there. Number 5, you can use u-substitution again. This is a great one where if you just see that you are undoing the chain rule here, your life is going to be so much easier. But we haven't done a lot of those with trig. So u is sine of theta, which means du is cosine of theta d theta, which means this integral is going to be the integral of cosine of theta times u to the negative 1st power times d theta over cosine theta. So those cosine thetas are going to go away. That's going to leave me with natural log of the absolute value of sine of theta plus c. All right, number 6. My first recommendation for you is to split this integral up. So x squared over x minus 4 over x dx. And then to simplify, this is x minus 4 over x dx. And then we can just integrate each term. So x is going to go to x squared over 2. Negative 4 over x is going to go to negative 4 natural log of the absolute value of x. And this is all going to have a plus c on it. So integrating with natural log, again, if the degree of the numerator is 1 less than the degree of the denominator, that's typically where you're going to see a natural log come in. You can use u-substitution if you need to on problems, but remember that if you can see how to undo the chain rule, manipulate it in that way. It's going to save you time. I'm encouraging that. All right, let's kind of review integration as a whole and start talking about some simplification techniques in general. So we're going to talk about 4 simplification techniques to help you out when you are integrating. So the first one is talking about division, and that is going to come into play when you have a polynomial and the degree of the numerator is greater than the degree of the denominator. And in that circumstance, the very first thing you're likely going to want to do is actually to perform that division. Now, you can use long division at any point in time if you have division like in this example here. You can also, if you're dividing by a binomial, you can use synthetic division, which I prefer personally, even though synthetic division doesn't work all the time. So I'm going to go ahead and set that up using the coefficients. So 1, there is no x squared term. The x coefficient is -6. The constant is 20. And I'm going to go ahead and perform that synthetic division. 25 minus 6 is going to give me 19. -5 times 19 is -95. This is going to give me -115. And something I want to point out to you is that when you have a remainder, this is going to basically be a part of natural log when you actually integrate it. So let's look at what we have now. Now we can say this is the integral. Remember, this was x to the third, so when I divide, this 1 is the coefficient of x squared. So of x squared minus 5x plus 19 plus or minus -115 over the thing we were dividing by, x plus 5, all of this dx. And now I can integrate. So using the power rule, x squared is going to go to x to the third over 3 minus 5x squared over 2 plus 19x minus 115 natural log of the absolute value of x plus 5 plus c. I'm going to try and box that. Sorry, it's a little hard to read. There we go. The next method, so that method, division, comes into play when the degree of the numerator is greater than the degree of the denominator. This is a great first step in that particular situation. U-substitution is obviously a strategy that works pretty often. And just as a reminder, when you're using u-substitution, you're setting one function equal to u, and then you are taking the derivative of that. So here, I'm going to do this one in green. I would probably let u equal natural log of x. That's the more complicated thing that I want to get rid of. That means that du is going to be equal to 1 over x dx, which means that dx is equal to du times x. So this is also sort of a reversing the chain rule situation, which you can do without u-substitution, but I'm going to do it using u-substitution just so you can see it. So this is going to become the integral of 1 over x times u to the power of -1 times du x. So these x's are going to divide out. So I'm going to get u to the negative first power, or even just the integral of 1 over u du, which is natural log of the absolute value of u plus c. And don't forget to plug back in what your u was to begin with, which was natural log of x. So we have the natural log of the natural log of x, absolute value, plus c. Now we're going to talk about two other u-substitution styles that involve a little bit more of intricity. So this first u-substitution that we used for the green could have been done using just reversing the chain rule, which is obviously a simplification technique as well. Change of variable number 1 is going to be u-substitution where you also have to solve for x. So here on this problem, I'm going to let u equal x plus 1, which means that du is going to equal dx. So if I just tried to rewrite this as is, I would have 2x times u to the negative second power times du. And I have a problem here. My problem is that I don't know, I'm going to move the 2 in front. My problem here is that I can't have an x, which means I need to take this expression and solve for x. That's going to be u minus 1. So I have u minus 1 times u to the negative first power du. So this is a change of variable number 1 for u-substitution strategy. So now I could, this is a -2. I can multiply u to the negative second power. That's going to give me u to the negative first power minus u to the negative second power du. And I can integrate this. This is going to be 2 times the natural log of the absolute value of u minus, we can just use the power rule for u to the negative second power. So minus u to the negative first power divided by -1. So let's make that plus, and I'm going to bring my 2 along for the ride. So plus 2u to the negative first power plus c. And then don't forget, as always, we need to put x back in. So this is 2 times the natural log of the absolute value of x plus 1 plus 2 over, or 2 times to the negative power, 2 over x plus 1 plus c. And then the very last strategy that we're going to talk about is change of variable number 2. And this is where you not only have to use u substitution, but you have to solve for x and potentially also dx. Okay. So let's look at this change of variable number 2 situation here. I'm going to let u equal what's in the denominator. So u is going to equal, actually let's use this space over here. U is going to equal 1 plus the square root of 2x, or 2x to the power of 1/2, which means that du is going to equal 1/2 times 2 times 2x to the negative 1/2 power dx. So all these, this is going to go away. So now if I solve for dx here, I'm going to get that dx is equal to, if this was to the power of negative 1/2, when I move it to the other side, it's going to become the power of positive 1/2. So 2x du, 2x to the positive 1/2 power. The problem is, based on this, I still have a problem. I still have a problem that if I try and set up this integral, I'm still going to have x connected with my du. That x is not going to multiply out at all. So what I can do is, this is a part of what I defined u to be. So look up here, u is equal to 1 plus that, which means that this is equal to u minus 1. So I can actually say that dx is equal to du times u minus 1. That is a substitution I can now complete and have everything in the integral in terms of u. So let's rewrite this integral. Sorry, this is a little scattered. This is going to be the integral of u to the negative first power times du times u minus 1. I can distribute here, so this is going to become u to the power of 0 minus u to the negative first power du. And then I can integrate, so this is going to become u minus natural log of the absolute value of u plus c. And then last but not least, I need to take this, sorry, this is so messy. I need to take this and I need to substitute back in what u is. Well, u is 1 plus 2x to the power of 1/2, or the square root of that, minus natural log of 1 plus, I'm going to just use square root because I'm running out of space. Close that absolute value plus c. There we go. I think that's a little easier to read. So before you start integrating, kind of look through and analyze and really think before you integrate. Think about what is a good approach to take to start. It's possible that you might choose wrong and you might have to go back and do it a different way, but at least thinking through before you get started is going to really help you choose a logical approach at the beginning. So let's look at some examples. So 7 through 11 are all problems that you now know how to integrate. What I want you to do is pause the video and first identify which method you think should be used on each problem. Then go back and actually complete each problem using that method. I'm going to just show all of the solutions worked out afterwards and kind of hit the key points. So go ahead and pause your video. So on 7, you're going to perform long division first. You're going to end up with the integral of 1 plus, or 1 minus, negative 4x over x squared plus 2. The 1 is going to be really easy to integrate. That's going to just give me x. The other part, I'm going to take the negative out. X times the integral of 4x over x squared plus 2 dx. My tip here is to use u substitution. The degree of the numerator is not greater than the degree of the denominator, so I'm going to use u substitution here. That's going to give me x minus the integral. You could also reverse the chain rule there for a faster approach, of 4x times u, not red, times u to the negative first power times du over 2x. So these x's and 2's are going to divide out, and I can just put a 2 here. So this is going to give me x minus 2 natural log of u, which I'm going to substitute back in x squared plus 2 plus c. This absolute value is a little redundant here. You don't need it, but it's definitely fine to keep it there. All right, number 2 is just going to be a straight u substitution problem. And when I say number 2, I mean number 8. So we can rewrite our integral, the integral of 1 over x times u to the negative third power du times negative x. So these x's are going to divide out. And I can just use the power rule for u. So I'm going to have negative u to the negative second over negative 2 plus c. So I can simplify and substitute back in. This is going to give me 1/2 times 2 minus natural log of x to the negative second power plus c. For number 9, we're going to use synthetic division, or you could use long division. That enables us to rewrite this as a polynomial with one term that is going to go to natural log. So when we integrate this, we're going to get x to the third over 3 minus 4x squared over 2, so minus 2x squared, plus 4x plus natural log of plus 2 natural log of the absolute value of x plus 1 plus c. Number 10 is a u-substitution problems, and since there are bounds, make sure that you change your bounds to be in terms of u as well. So when I rewrite this, I'm going to get the integral from 1 to 2 of u squared over x times du times x. So these x's are going to divide out. That's going to give us u to the third over 3 evaluated from 1 to 2, which is 8/3 minus 1/3, which is 7/3. Okay, number 11, we're going to have to do u sub with change variable number 1, because once we use u substitution, we're still going to have an x that we have to deal with. So go ahead, set u equal to x minus 2, and then go from there and you'll discover how you have to change x to be in terms of u, and also don't forget to change those bounds. So this is going to become the integral from 1 to 3 of x plus 1, but x is u plus 2, so u plus 2 plus 1 times u to the negative second power du. That's going to give me the integral from 1 to 3 of u plus 3, and I'm going to distribute that u to the negative second, so u to the negative first plus 3u to the negative second power du. When I integrate that, that's going to give me natural log of the absolute value of u minus 3 over u, and we're evaluating that from 1 to 3, which is going to give us natural log of 3 plus 2. All right, very last thing in this section of notes, we're going to talk about integrating with tangent and cotangent. So we're going to derive the integral of tangent of x using trig things that we already know. So we already know that tangent could be written as sine of x over cosine of x. So I can substitute that in. And then you could use u substitution here, but I'm not going to, because I'm going to reverse the chain rule. So if I make that sine of x negative and I throw a negative in front to even that out, I really just have to reverse the chain rule here, because the derivative of cosine is negative sine. So this is going to give me, this is equal to negative natural log of the absolute value of cosine of x plus c. So in case you didn't see where that came from, if you let u equal cosine of x, then du would equal negative sine of x. So you would end up with the integral of 1 over u du, negative the integral of 1 over u du. And that's how that would work. This works almost exactly the same way with cotangent. Cotangent could be rewritten as cosine of x over sine of x dx. And when we use u substitution or reverse the chain rule, this is going to become 1 over u, which means this is natural log of the absolute value of sine of x plus c. All right, why don't you go ahead and pause the video and try and work through these last 3 problems, and then I will work through them with you. So number 12, you can use u substitution, or you can just reverse the chain rule. So I'm going to throw a 2 in front of tangent, and I can do that because I'm throwing a 1/2 on the outside. That's going to give me negative 1/2 natural log of cosine of x plus c. Now my hint for you on number 13 is to remember that tangent squared of x is equal to secant squared x plus 1, and see if you can work through that. So we can change this to be secant squared x plus 1. We know that the derivative of the antiderivative of secant squared x is tangent of x. The antiderivative of 1 is x. and then don't forget your plus c. And on the very last problem, I'm going to recommend that you let u equal sine of x plus 2 and see if you can work through that one. So if u is sine of x minus 2 and du is then cosine of x dx, we can substitute this in to get cosine of x times u to the negative first power times du over cosine of x. And those cosines are going to divide out. So this is going to give us natural log of the absolute value of u plus c. And then we need to plug back in what u was, and u was sine of x minus 2. So the key things to remember in 5.4, when we are integrating with natural log, or when we are integrating 1 over u, we're getting natural log of the absolute value of u. And that absolute value comes into play to help out with the domain restrictions or the domain issues that we talked about in 5.1. Make sure that you can do that if there's a chain rule involved. Make sure you're thinking through each of the different simplification techniques, like using long division or synthetic division, using u-substitution, using the change of variable number 1 or number 2 in the cases that you need them. So remember, all of the things that you have learned about integration still apply even when we learn something new. You haven't lost one of the tools we learned in previous chapters. Looking forward to supporting you in class. Thanks for listening.